Hi guys, welcome to your Chapter 10 video, Part 1. This is the last chapter that we're going to look at with regard to regression line stuff. I think that if I can remember correctly, chapters 11, 12, and 13 are all on surveys, experiments, and observational studies, and that's a huge departure from what we're doing here in chapters. Let's see, it's been 7 through 10. Chapter 7 was the correlation coefficient. Chapter 8, we built the regression line. Chapter 9, we talked about how to be smart about when applying the regression line and how to make sure that we had a process through which we could identify a regression line given a scatter plot. Here in Chapter 10, it's really about fixing data that would not work well with the regression line natively or naturally. This ladder of powers is, let's start with the basics. It's really important. Duh. It's something that honestly you need to have memorized going into your Unit 2 exam, which will be after fall break, perhaps a week and a half after fall break. That would be my best guess. Based upon how you guys are progressing, your progress is good, and based upon what you guys have done so far. This needs to be memorized. What needs to be memorized specifically? Well, not the comment, not the third column, but the power number and the name or the identification of your Y associated with that power. So, first of all, let me say the following. This ladder of powers, I've given this as a Word document in the past that was one side, front, and back. Your rungs in this ladder are set up so that power 2 is a rung, power 1 is a rung, power 1/2, etc., is a rung. The top of the ladder is going to be power 2, which I started the arrows with. Then it wraps around, okay? So if you've tried rung 0 for re-expression in your data, and we'll talk about what that means here shortly, and that's not working, you would continue on this ladder going to rung -1/2, and if that still hasn't fixed things, you would try rung -1. Okay, so it's a wraparound vertical ladder here. It's not two separate tables, it's just one table. What is going on here? Well, the ladder of powers is helping us to identify how you can plug in your Y values, the actual Y values, not the predicted, the actual Y values into your scatter plot, having re-expressed them to make your scatter plot straighter, okay? So these powers of 2, 1, 1/2, 0, -1/2, and -1 are re-expressions for all the power of your Y value. So let's say that, let's start with the basics. You guys have been working with this rung that's still highlighted the whole time, at least since Chapter 8 when we identified the regression line. Rung 1 is the power of 1 for your Y hat, so this would be Y hat to the first power equals mx plus b, okay? That's just the regression line, Y hat equals mx plus b. That's where you start every scatter plot, okay? So there's nothing new there, so that's rung 1. Rung 1/2, for instance, just directly below that rung 1 would be the following. That would be Y hat to the 1/2 power, which is a fancy way of saying equals mx plus b, which is a fancy way of talking about the square root of Y hat, radical Y hat equals mx plus b, okay? So that's that guy, etc., etc. Now notice rung 0 here, for instance, and rungs -1/2 and -1 are in the same boat. If I was to mean this literally, that these rungs are strictly just the exponents on Y hat, instead of rung 0 being log of Y hat as it's identified here in that second column. I mean, that's not mathematically sound. It's not really that Y to the 0th power is the same thing as the log of Y. It would be this. We'll write the arrow. It would be this. Y hat to the 0th power equals mx plus b. Okay? But really, the ladder of powers is nice for two reasons. if you memorize it, and you really should, it's going to give you quick, easy re-expressions on your y values so you can make your scatter plot straight. But it's basically a memory tool the way they've set it up here. Rung 0 is easier than saying you've got rungs of 2, 1 and 1/2. Oh, and then you got the log rung. No, that's harder to remember. Same thing here with this negative 1/2. Y to the negative 1/2 power would just be 1 over the square root of y instead of the negative 1 over the square root of y. Okay? Now, let's see. I should come back to that. Okay? I'm going to talk about why you've got your negative signs here. Oh, blocked that, or blurted that out, cut it out rather. Why you have your negative signs after we've seen a few examples. This is best explained in context. You could go about, and I've tried to go about, making this more mathematical than it needs to be, and it really doesn't do anyone any good to do that. Because the ladder of powers is a strictly trial and error process. You always start by looking at the data that you've got. Rung 1, okay? If your data is not straight, you try something else. If your data is not straight, you then try rung 0. That's your second step if you've not fixed anything. If that works, great. If it's not quite, if the residuals plot is not randomized, if your scatter plot's not straight, then you bounce around on the ladder from there. So let me show you how this works. You've got example 1 here. Ball players have been signing ever larger contracts. The highest salaries, millions of dollars per year. For some notable players are given in the following at right. For the data at right, we want to create a scatter plot to determine the appropriateness of the linear model. If a linear model doesn't seem appropriate, we're going to use the ladder of powers to re-express the data and still get a linear model from this, okay? So you've got, I don't know, let's see if I can, I don't know these names. Oh, baseball players, based upon Ken Griffey Jr. here. So we're talking about baseball players, the year for some given salary that they made. It's not necessarily starting salary. Maybe their peak salary is given in the third column. So we've got, notice, 2 quantitative variables, year and salary. And on your Chapter 7 quiz, a lot of you guys were forgetting, you made mistakes on the first piece. Chapter 7 quiz asked about a correlation between eye color and customer satisfaction. Both of those variables as about, I think, 1/4 of you observed. Not quantitative. Everything we're doing with this regression line with the correlation coefficient hinges upon quantitative data. Those are qualitative variables, eye color and customer satisfaction. So wanted to get that in. We've got the calculator set up already. Let me reopen the file I saved here with the data already. So in L1 and L2, you've got your years and your salary in millions of dollars, okay? And first thing we're going to do, the method I gave you guys in Chapter 9 in their second video of first trying the scatter plot, seeing if the quantitative data condition is met, seeing if there are outliers, seeing if the straight enough condition is met. That is not changing in this Chapter 1 bit, okay? So plot 1, we're plotting L1, or X data, versus, in this case, we'll go with L2, our Y data. We'll go zoom stat. And clearly, I mean, there's no real need to even look at the residuals plot in this case. We're going to do that anyway just for the sake of being thorough, but you can already see that the data is curved. So this is what I want to do. Now that we know a little bit about the ladder of powers, let's do the following. We have tried, or we're looking at the model that would be y hat equals mx plus b. That's rung 1, where your exponent here is 1, okay? So for this particular model, the scatter plot is curved with relatively strong association, okay? We have not checked the residuals plot yet. We will do that, and we will talk about R squared. This is the chapter where R squared becomes valuable. So, we are going to get the residuals plot, remember, we have to go to linear regression. The linear regression function not only gives you your linear model, which we don't necessarily want. We don't care about that just yet because the data is not straight. We're not going to use this model. But we do want residuals, okay? And linreg gives us the residuals. So we're going to go L1, comma, L2, enter. Remember, the calculator is doing some hidden things here. There's your R-squared value of 75.81%. Okay, so we're accounting for, you guys are, I've seen a lot of trouble. I think it's difficult for you to interpret R-squared correctly. R-squared in this case, and in every case, means that 75.81% of the variability that you see in your Y data is accounted for by the regression line given here in linreg in this particular case. Okay, so not a really strong R-squared value, not horrible, but obviously the data is not straight. We're going to take out our magnifying glass, the residuals plot, to confirm that. XList is not changing. We keep that the same for residuals plots. We're going to go second list, scroll up to resid, hit enter, zoom stat again to focus in on the data, and it's absolutely clear there too in the residuals plot that you have a curved association in your data, not curved correlation. Correlation is a statistic. Association is the description of the what the picture looks like. Correlation, remember, is just a number between -1 and +1. Okay, so lots of kind of crappy stuff going on if we use the y hat equals mx plus b model. Okay, so last slide we said in general your rung 0 tends to be a good fix, the log of your y values. Let me show you how you can do that. This is not something where you have to go through, and if salary in this case is our y values, we're predicting salary, that's your response variable based upon year, your explanatory. You do not go through one by one and take the log of all these numbers, okay? There's a much easier way to do that. I'm going to quit out of my scatter plot, clear that, and I will say I want the log of, you got to keep track of which list is your y list. In this case, I've tried to keep it as generic as possible. L2 is my y list. So I'm taking the log of all my L2 data. That will take the log of each individual number of the 13 different player salaries there. And I'm going to hit store here and store that in a new list. Okay, I'm going to choose L3 based upon the fact that I'm not solving another problem simultaneously, so I can just I can store L2 and L3. If I wanted to store more, I could store L2 and L4, etc., etc. We'll hit enter on that. It tells you what the log of this, the data that was in L2 has become. You don't really need this. It's kind of funky. To the best of my knowledge, you can't scroll through. Oh no, yeah you can. My mistake. You can scroll through it, but it's a really clunky way to see the list. If you really want to see the list and you do not have to, you can check that it's there by going back to stat edit. There's your re-expression for your y values. Okay, let's see if this re-expression has fixed anything. We're going to go back to the scatter plot. That's always where you start. The X list has not changed. I took the log of salaries. I did not change my year, so L1 is the same. Now I don't want resids. That would be the resids of the original model that I was building from. Okay, I just stored the log of my y values in L3. We'll hit enter on that. We'll do another zoom stat, and voila, we've got a much straighter scatter plot. That looks really good. So make a note for yourself, because I've seen students too often forget where they're at in this trial and error process. I would write a couple of things down, these 3 things down as you're going from model to model. Okay, so we are trying rung 0, which is log of y hat equals mx plus b. All right, and so for the scatter plot, we're seeing a straight association. And it does look to be, if I remember correctly, it looks to be strong. All right, so let's check out the residuals plot and R squared as well and see what we get from these. Okay, so we're going to go back to linreg. We can quit out of this. We can clear that if that's visually confusing. Stat, calc, down to linreg, We are going to go second L1. X list again has not changed. And be careful, we are using L3 for Y. And if it would help, you might want to, in parentheses, put the list name over here as you go through this trial and error process. We'll hit enter on that. There's our R-squared value, significantly improved, 96.22%. That's an awesome R-squared. So 96.22% of the variability that we're seeing in the Y data now, re-expressed though it may be, is accounted for by this log regression line, whereas the plain Jane Y hat regression line did a much worse job of coming close to the data. All right, residuals plot. So again, residuals are being secretly stored into your residuals list. X list has not changed. L3 now we want to say should be resid. We'll hit enter on that. We'll do a zoom stat. And there you go. You've got, I don't know, maybe you could really nitpick and say that there's a little bit of curvature there in your residual plot. However, compared to the last one we saw, we see a relatively randomized residuals plot. Okay, so that's an improvement. R squared was better. The scatter plot was better. The residuals plot had less of the pattern. Those are all good things. Okay, now here's why it's truly trial and error. You don't stop when you find something that is pretty good. Okay, you then try. You try to see if you can find further improvement. Okay, we know now that rung 0 here is awesome for the data in the slide right after this. Okay, we're gonna go to. Oh, okay. Let me say the following. We started here, okay, and we saw that things were bad. We went this direction. We went down the ladder and saw improvement. There is no reason to go back up here to power 2, okay? The direction of movement through the ladder is helpful to take note of, okay? You always start with rung 1. We jumped down the ladder and we saw improvement, so there's no reason to go back up the ladder. In the opposite direction from where we've already started. However, we did note a little bit of patternness in the residuals plot. We're going to try both rung 1/2 here and rung -1/2 to see if we can narrow in on even a better model than what we've got with rung 0. Okay, so let's just start with rung 1/2 first. So what we're going to do, we're now talking about the model that would look like the following. Let me pull the calculator back up. Rung 1/2 is square root of y. So this model, if it's a good one, would be the following. Y hat equals m x plus b. We're going to make note of the scatter plot, the residuals plot, and your R squared. Okay? All right, let's see what we've got. So, let me quit out of this again, clear that guy. We are going to do square root of, careful as to which list you want to take the square root of. We are taking the square root of the original y values here. This is not the log of y, the original y values that we had already had. So we're going to use the square root of L2, this second list, just as before we'd taken the log of L2. We're changing the original data. We're not saying, okay, we changed the data from here to here. Now let's use this change data to make a new model. Nope. All of these models are based upon the original y values in that second column. Okay. So this is the square root of L2, close parentheses. We're going to store this. We've already used L3, and we don't want to get rid of L3 because it may be the best we can find. So we're going to store this in L4 next. Okay. So we're using additional lists as we go across. You will use a lot of lists if you're checking very thoroughly, okay? Okay, so we've got our new Y data. X list has not changed. Resid is now, we're going to change that to L4. We'll go zoom stat and see what happens. And it looks like there might be some curvature, which would kind of make sense because we went from original rung 1 to rung 0 and saw significant improvement. We're now moving back up the ladder just a little bit at rung 1/2. Closer to where we started, and it may be the case that given our original data was strongly curved, we may see that rung 1/2 is not quite good enough. Rung 0 may be the best that we've got. All right, so there's your data. Scatter plot has some minor curvature. And, oh, that is not a V. Minor curvature, and I'm seeing a strong association in the data. Let's check out the residuals plot again by going to Stat, Calc, LinReg. We're going to use L1, comma, L4, our re-expressed Y data. And we're seeing an R squared that has fallen from rung 0. So, okay, this re-expression may not be a great one. That's 89.41%. Okay. In your residuals plot, remember that residual list is being saved each new time you use linreg, and it's a new residuals list every time you use linreg, assuming you're changing your variables when you do that. So we're going to go second list here, up to resid, hit enter, zoom stat, and it's clearly patterned. Okay. Curved. All right. So far, I'm going to put a star beside this guy. This is the best we can find as of yet. Let me check the time on this. Sheesh, man. This is a long process. I'm not going to beat around the bush there. This will take some time if you're doing it well. However, explaining and doing the problems takes about double the time versus just doing them. All right, so rung 1/2 did not help as much as rung 0. Let's go beyond rung 0. If negative 1/2, rung negative 1/2 does not improve on rung 0, there's no reason to go down further, okay? Because the way in which each of these rungs improves upon the Y values is a progression. That's why they're arranged in this way. There's no reason to check negative 1 if negative 1/2 is not helping over rung 0. All right, so let's put over rung negative 1 is, okay, let's put to the left here, negative 1 over the square root of Y hat equals mx plus b. Okay, let's check the scatter plot. We have used lists 2, 3, 4, and we re-express the data here. The original Y values, we're going to use list 5 this time. Let me clear this guy out. So if that is negative 1 over divided by the square root of your Y values, which are in L2, double close parentheses, we're going to store this, and I think we had said L5. Okay, and again, it's giving you the data if you care to see it. We're going to go back to the scatter plot first thing. Plot 1's on. X list again has not changed. Now we're looking at L5. We're going to zoom stat, and I see curvature. Okay, so we see curvature. But notice it's curvature that is I want to say it's curving downwards. It's concave down rather than concave up. For those of you who have taken calculus or pre-calculus, this would, if you extended the curve, it would look something like this guy right here. Okay. Let's. Yep, I'm going to delete that. Oh. There we go. Okay. So, scatter plot's curved. Let's check the residuals plot just to be thorough. We're going to go again, stat, calc, linreg to get a residual list here and get L, or R squared rather, in the process. L1 now is your X list that has not changed. L5 is your new re-expressed Y values. So R squared is 92.6%, which is not bad. It's not as good as the other one we've seen. 92.59%. Be consistent with those 4 non-zero digits for all my R squareds. The residuals plot, going back to stat plot. Why is this beeping at me? Oh, okay, I don't know. We'll use a residual list for our Y variables, or Y variable rather. Hit enter on that. Zoom stat, sees. We've got, again, that downward curvature. Okay, so the best fix on the data that we saw was that log of y hat equals mx plus b. Obviously, if you were being asked for the linear model, you're going to say not log of y hat equals mx plus b. You need to know what your slope and y-intercept are. So remembering that we had these y values were L2. These y values were L3. We're going to use linreg one more time. Now, again, I told you this is a long process, but hopefully you can see the strong pattern as we go through this. You're doing three things every time, checking scatter plot, residual plot, r-squared. And, okay, so our slope was 0.0573. Times your x variable, which is year in this case, minus your y-intercept of 113.5. Okay, so that's the best best model that we could come up with. It fixed the residuals plot fairly well, had a very high r-squared value, and there you go. We're going to skip the next problem based solely upon the fact that this process, it is time consuming, and we're going to get plenty of practice with these sorts of problems in class. I'll be bouncing around as I tend to do, helping you guys figure out how to use the ladder of powers further and answering questions as best I can. The second video will practice more of this stuff, and we might go through it a little bit faster now that you've seen how to do this one time. So, second problem here we're going to skip. I just don't want to go to the 50-minute mark on this video, and I know that's what's going to happen if we do that problem. So, we've talked about re-expressing how to find your model using this ladder of powers. Suppose I ask you to determine the y value the regression line predicts when I give input of x equals 2, and the regression line is, what was I going to use here? Log of y hat equals 4x plus 3. Okay, let's say that was the best re-expression of y values that we found. So that's our linear model. How would you go about finding the y value the regression line predicts? Because what we don't want to do, 2 years ago is when I really saw this. Last year's class didn't make this mistake too often. First year teaching, I guess I wasn't clear on this. You don't want to say the following. You want to say log of y hat equals 4 times your 2 plus 3 based upon 2 being your input for x. You don't want to say that your predicted y value is just 8 plus 3 or 11, okay? That's not how this works. We're changing how the y values look to use this linear model that we've seen since chapter 7. But now if you want the y hat, the y value the regression line predicts, you've got a little bit more work to do, okay? So remember, anytime I write log of some variable, that is a hidden log base 10. Hidden log base 10. We can rewrite this, okay? You can, actually students tend to prefer the following. Don't worry about the rewrite. If log base 10 of y is equal to 11, we can do the following. We can say, okay, 10 raised to that power must be the same as 10 raised to this power. Why? Because those two powers are equal. We just said that in the equation before we threw in the 10s, the bases of 10 here. When I take a power, when the base, let me circle the important things here. When the base and the log base whatever are the same here, those cancel out. This guy's gone, and I have just y hat equals 10 to the 11th power, which is like 100 billion. 100,000 million billion. Yeah, there we go. 11 zeros following that 1, okay? That's really how you need to conclude finding your y hat, your predicted y values here. So there's your first example, okay? Let's take a look at another. Make just a little bit of room here. Let's say our regression line was not log of y hat equals 4x plus 3. Let's say the regression line that best fixed the data was negative 1 over the square root of y hat equals 4x plus 3, so we're not changing the right side here at all. Same deal. You're going to plug in your input. If we want to know the y value predicted, we're going to say negative 1 over the square root of our y hat is equal to 4 times 2 plus your 3. So this would be negative 1 over the square root equals 11. Okay, well, multiply, I wouldn't multiply by the reciprocal, although you could. Just multiply both sides by your square root of y hat. So you've got negative 1 equals 11 radical y, which takes you to negative 1 over 11, dividing both sides by 11, is equal to the square root of y hat. Let me make sure I get those hats in there. Yep. Square each side to get rid of the radical. No biggie there. So you've got 1 over 121 is equal to y hat. Okay? So again, be careful. 2 years ago, I saw a lot of students make the mistake of thinking that whatever's on the left side is your predicted y value. Not the case. You're re-expressing the data so that it works for the model. That means you got a little bit of tweaking if you plug in your x value to find what your y hat, your predicted y value actually is. All right, now considerations when using the ladder of powers. This is going to wrap it up for these notes. Let's say I am using, which rung would this be? This would be rung 2, and I have the following. Let's say that I have, once I plugged in my x value, like we had done in the first slide, I get something of the form y hat squared. Remember, squaring is your rung 2 in the ladder powers equals to some a, some constant. Well, if you're going to try and find this y hat value here, the only way you can do that is to take the square root of both sides. And so there's a limitation on what a can be. A cannot be equal to a negative, right? You can't take the square root of a negative unless you want imaginary, or I was going to say unreal, imaginary numbers. You don't want imaginary numbers. We're trying to keep it real here. We're trying to keep things making sense, okay? So be careful when you're using rung 2 that you're not setting yourself up to take the square root of both sides. That's not going to work. It just won't work for you. All right, let's say I looked at rung 0 here, and I had the log of y hat equals 2 some constant. Well, remember, log, whoop, that's sloppy. Log of something when it's base 10 like that, equaling to a number, that means the same as the following. 10 raised to the power of a is equal to y hat. So, you cannot have y values here in your scatter plot. You cannot have y values that are, let's write the following. They can't be equal to 0, and they can't be equal to a negative number, okay? Because if your y values are negative, then you're saying 10 raised to some power is going to give you a negative. That never works. Plug in negative a for your exponent, you're going to get something really tiny, really close to 0, but that equation will never be negative for y hat. Can't be. It cannot be if you're wanting to get an answer for a, or vice versa. So what does that mean you do? If your y values in the data are negative, add some constant to them. So that you would have, instead of say, let's say you had found log of y hat equals 4x plus 3, using what we've seen above. Well, if that 4x plus 3 is giving you negative numbers, you can instead say the following. You can say, well, let's change it to log of y hat equals 4x plus, I don't know, 103, okay? Add some constant so that your y values are suddenly all positive. Now, I know this is abstract, but it's still valuable. You're going to see why I'm talking about this when we get to the homework, okay? Couple other things. If you are looking at rung 1/2, which would be the square root of y hat equals to some constant, here your y values again can't be equal to a negative. You cannot take the square root of a negative number. So there too, you would add something to all your y values when you're setting up your lists in your calculator, and that would fix the problem. Rung -1/2, similar to that, that is -1 over the square root of y hat equal to some constant. If you've plugged in your x and you get a on the other side, there too, your y values can't be equal to a negative, but additionally they can't be equal to 0. You can't take a 0 in the denominator. You're going to get an undefined answer. 1 over 0 gives you nothing that we can make sense of in math. Last rung here, rung -1. Let's say you plugged in again for x. You have -1 over y hat equal to some constant, some number on the other side. Your y values simply can't be equal to 0. Okay, so what's the takeaway here? From all that we've talked about regarding rungs 2, 0, 1/2, -1/2, and -1, I would, in general, notice the repetition with negative values and 0 being a pain in the butt. Okay? I would, if you're given data, let's make this less hypothetical, let's make this more contextual here. Let's say, now I know this won't make sense, but let's say your salary in millions was negative, okay? You had Nolan Ryan being paid -$1 million, George Foster being paid -$2.04 million. Just add some number to your y values so that they're positive, they're big enough that you're not going to have problems when you're using the ladder powers. And that's all I'm going to say about that for now. I want you guys to sort of see that in context next class. We will absolutely have a video quiz over this. This is a big idea. However, I should mention now that the AP exam really doesn't test a whole lot over ladder of powers. And my guess as to why they do that, 2 reasons. It's hard to remember these things long term. All your rungs, they're hard to recall. And they are not going to make their reference sheet on the AP exam an additional page long just so that you can be able to do a few more extra problems on the AP exam. This is a small little sliver of the entire course. Secondly, it takes so long. I don't think that it's a good use of your time, either in this class. On the test, for instance, I can assure you now that you're only going to have one re-expression of your y variable problem on the Unit 2 exam. Just one. Now remember, I'm only giving 5 problems or so, so you will be tested over it, but it's just not a big deal. It's like sometimes you'll go an entire year on the AP exam and none of this will show up.